All right, this is going to be an optional video. The reason I'm doing this is because I know that line integrals are new and I don't want you to feel like you haven't seen enough examples of them. And we had to go very quickly with the vectors to get through everything. So this is just in case you want to see some more examples. But before you get kind of like worried about the fact that you haven't seen a whole lot of these vectors, vector line integrals, I want you to be able to recognize that vector valued line integrals aren't all that different from when we did scalar valued line integrals. And the way they're the same is because the integral of f dot dr is actually just the same as looking at f dx plus fy dy plus fz dz for vector value f equal to f sub x in the x component, f sub y in the y component, f sub z in the z component. And the way we're going to see that is by going back to this example, y dx plus x dy over that curve. And I think curve is a picture in your book, so I can pull that up. Separately. Okay. So we're going to think again about this example over the curve C, looking at y dx plus x dy for this curve. Negative 3, 3 down a line, and then to the origin, up to the point 2, 1, using the curve y equal x to the fourth over 16. Okay, so what we ended up doing was converting this into integral over the bounds t of kind of x prime of t dt times our parameterization for y plus parameterization for x, y prime of t dt. But if we had had f equal to yx and r equal to our parameterization, then what would happen is our y would go there and our x would go there in our dot product. And the derivatives of our parameterization, so exactly x prime, y prime, would in our dot product end up there and there. And so we're actually going to go ahead and do this problem as if it was given to you as a vector problem. And again, we'll do it both ways. We'll do it fundamental theorem way and we'll do it parameterization way so that you can see another example, but also see that it's no more difficult than the example we did earlier of a vector value function with dx dy given to us. So our example is going to be to integrate C f dot dr over this curve again. It's getting worse and worse every time I draw it, but that's okay. Negative 3 to 3, 2 to 1. Y equal minus x there, and y equal x to the fourth over 16 there. For f equal to y comma x. And again, we're going to do this the two different ways. So the first way is fundamental theorem way. And f equal to yx is a conservative vector field. That means I'm asking myself, can f be written as a gradient vector? And I'm just going to try to find f that satisfies this. So that means that I have the system of equations, y equal to df dx, x equal to df dy, which gives me the two integration problems, f the integral of y dx and f the integral of x dy. This is the way that we talked about setting up problems where you need to find the potential function. And if that's still iffy for you, don't worry about it. You're going to get more practice with it as we go through this section, because this tends to be an easy way to solve line integral problems. This is, again, one of those silly ones where both the parts exactly match each other. Makes for good line integral problems. So the integral of y with respect to x is y times x plus an unknown constant that could depend on y. And the integral of x with respect to y is x times y plus an unknown constant that could depend on x. Since I found the same term for both of these and nothing else, I know that my function f is just equal to x times y. And these unknown constants I didn't have to worry about for this particular problem. So I know that my line integral is just equal to f at the endpoint, 2, 1, minus f at the starting point, minus 3, 3, for f equal to xy. So f is equal to 2 times 1 minus 3 times 3. So that's 2 plus 9 is 11. And back when we did this example, I think I said it wasn't a good use of your time to see me solve the integrals. So we cannot check that that's correct, I don't think. But hopefully it is. If you went and checked that, hopefully that's what you got. And we're also going to do this the part B way, so we can at least check that we get 11 that way as well. So now suppose your first thought wasn't to say, I'm given a vector field, I'll try to find a potential function that generates that as a gradient. Instead, you're like, I know that parameterization solves every line integral problem, so I'm going to go ahead and do that because it always works. And it does. Unfortunately, this is that curve that we had to break up into two different parameterizations, so we are going to have to go ahead and do that. But I'm not going to take your time, again, showing you the two different parameterizations. I'm just going to recall that we had x equal to t, y equal to minus t for negative 3 less than or equal to t less than or equal to 0. And then x equal to t, y equal to t to the 4th over 16, that time for 0 less than or equal to t less than or equal to 2. And so given those two different curves, we can kind of break up our problem into two parts. So for the first curve, r is equal to t minus t. That means r prime is equal to 1 minus 1. And our f, which was yx before, is going to be equal to minus t for y and t for x. And so the integral that we have to set up is over the bounds, minus 3 to 0, dotting f that only depends on t with r prime that only depends on t, integrating with respect to t. We'll evaluate that in a second. But we'll follow the exact same process for C2. Exact same process you'll set up any parameterizing vector value function line integral problems. We're going to say this is our parameterization. We pack it inside a vector R, where our x component goes first and then our y component goes second. Maybe we leave room for a z component if we have to. And then we just compute the derivative. So I say r prime is 1, 4t cubed over 16. So that ends up being 1t cubed over 4. I just canceled out the 4 and the 16. And then I substitute into f, which used to be yx, the parameterized values that only depend on t. So I get t to the 4th over 16 from y in the first component, and then t from x in the second component. And I'll set up my integral over the t bounds I was given, 0 to 2, of f t to the 4th over 16 comma t, dotted with r prime, 1 t cubed over 4 dt. And so setting up these parameterization problems is pretty formulaic. You can see that these are just the steps you follow. Whatever order you prefer is fine. The hardest part is finding the parameterization. And it does end up being a bit longer than just finding the potential function. So our c f dot dr is given by c1 f dot dr plus c2 f dot dr. And we just found those two pieces. So we said we go from minus 3 to 0 of minus tt dotted with 1 minus 1 dt. And then for C2, we go from 0 up to 2. And we're looking at t to the 4th over 16 comma t dotted with 1 t cubed over 4, I think. 4th over 16 comma t. Okay, so all I've done is I've taken what we found down here following our parameterization process and just put it all together here in one line where we're saying we wanted to find the line integral over all of C. We knew we had to break it up into the straight line and curvy line part. And here's what happens when we just follow the steps of the process for those two parts. Now I'm looking at integrals that depend only on time. I integrate with respect to time, and it's a 1D integral. The only tricky part is that I have vectors inside, but I'm taking a dot product, so it's fine. And from that dot product, I get minus t, so that gives me minus 2t dt right there. Actually, I'll do it in 2 steps because I don't want to be skipping too much. And then in the second one, I take my dot product, I get t to the 4th over 16 plus t times t cubed, so that's t to the 4th over 4 dt. And real quick, I want to go back to when we did this problem the first time, because the reason I picked this was because I wanted you to see that the vector valued function problems aren't that challenging or different from what we were doing before. So I tried to make the argument that the problem we were solving was exactly the same as this one. And hopefully it started to feel really familiar as we worked through it. And even if you look at what we got before, we had this minus t, that's showing up for us over here. Here's our minus t. Our x prime, y prime are giving us those values. And then for the second integral, there was a t to the fourth over 16 plus 4t to the fourth over 16. Oops. And we have that right here, t to the fourth over 16, t to the fourth over 4 was my simplification of 4t to the fourth over 16. So we really do end up in exactly the same place because we're solving the same problem. It's just represented differently. Vectors are a nice compact way to represent things. That dx, dy, dz format is just a longer representation. So when I add everything together, I get minus 2t dt right here, plus integral from 0 to t. That's 4t to the fourth over 16 plus 1t to the fourth over 16. So 5t to the fourth over 16 dt. That was just adding fractions right there. And I told you this time I would actually evaluate it. So let's do that. Let's see, that becomes minus t squared evaluated from minus 3 to 0, because t becomes t squared, and I would have to divide by a half to cancel out that 2. And then t to the fourth becomes t to the fifth. 5 is fine, over 16, 0 to 2. And so I'm going to get minus, we're going to do the two parts separately, minus 0 squared minus negative 3 squared plus 2 to the fifth over 16 minus 0 to the fifth over 16. And I'm just going to shift this down because I don't feel like going to a new page for arithmetic. So that's 0 plus 9 plus 2 times 2 is 4. 4 times 4 is 16 times 2 is 32 over 16. Let me just check that. I think that's correct. Minus 0. So I'm looking at 9 plus 2 is 11, which should be same thing I got on that page. So this is just another example of the different processes we can use to solve vector value line integrals, and hopefully helping you recognize that really all the different ways that we talked about line integrals in this section are connected, even though the representations were different. And so that I hope these extra examples kind of bridge those gaps for you. If it didn't, don't worry, we're going to get so much more practice as the section